Friends, we're going to be talking about industrial protocols for Pentesters. Let me introduce myself. My name is Alexander Timuri. I work for Positive Technologies. I work in the penetration testing department. I'm interested in popular SCADA systems and the industrial protocols they rely upon. My name is Dmitry Yefanov. I work for the same company, but in a different department. I'm responsible for development of security tools. I'm interested in network protocols, binary, text, proprietary, open, you name it. I'm involved in the SCADA research as a protocol guy. Our initial plan was to spend quite some time with you talking about ERP, MES and SCADA systems, but then we decided to just bypass the whole thing and briefly tell you that SCADA and ICS systems are now used extensively around the world, from production of Guinness and the cars that all of us love, to production of food, in fact, you will see lots of ICS deployed in plants, factories. In many cases, you will see ICS used to automate traffic controls, for example. So in our presentation, we are going to tell you about the most popular industrial protocols such as Modbus, S7, which is a proprietary Siemens protocol. Next, we shall tell you about authentication and protection available for S7 and other protocols. Next, we'll tell you about Profinet. We also expect to tell you about DMP3, but in our workshops, Dmitry covered it extensively, so we are not going to do it today. The world of industrial protocols is quite diverse. In this slide, you will see some of the key protocols. You will see that behind these protocols we see some key industrial leaders such as Schneider Electric, Siemens, Rockwell, Mitsubishi. DNP3 is also promoted by Siemens. In the same chart, you will see distribution of these protocols. We'll start with Modbus. Indeed, we are going to tell you more about Modbus. In fact, it has been discussed quite a lot lately. There are lots of tools for Modbus, but we should start from the very beginning. This is the oldest industrial protocol around, and we would assume that it's more widespread than others. So Modicon first published its specs in 1979. Now Modicon is called Schneider Electric. Since 1979, this protocol has been slowly rising into popularity, and it pretty quickly became the de facto standard. And this is the case probably because this is a pretty laconic, simple protocol. It's pretty easy to deploy. Now is used by such large companies as Schneider Electric. Well, you can't blame them, they actually developed it. But also ABB, Emerson, Advanced Microcontrols, they also support it. Their logic is that they are a large company, they should support popular protocols. And also it is used by Chinese no-names, because obviously they need some protocol, right? In fact, all vendors you can find in the market for industrial protocols support Modbus, at least because they want to be compatible with other tools. Let's look at what Modbus was like in the 20th century. Obviously, back then TCP/IP was not on the cards, so it went on RS-485 and RS-232, and therefore connectivity was usually limited to a specific workshop. In the 21st century, obviously, Modbus saw substantial evolution. And Modbus was finally put over TCP/IP. In fact, many vendors will show you something like that now. You see the IP network cloud there, and this is obviously the humblest statement here, because some vendors call it the internet or even cloud, and SCADA in a cloud sounds very scary to me. And for the life of me, I can't understand why you would do that. Okay, this is what a query in Modbus is going to look like. In fact, the format for the response is going to be pretty much the same. They use the standard 502 port in TCP. And the only fields we care about are the unit ID, function code, and data. Data obviously will depend on the operation, on the function. Unit ID is not used for protection, it is only used for addressing, which means that Modbus devices can be connected directly to a TCP network, then they're going to ignore it, or they can sit behind a gateway. In that case, they will be connected to the gateway via RS-232. In that case, the gateway, the router, is going to use their unit ID for routing. Also, please know that Modbus only works in query response mode. They usually tell you that you need to establish connection and avoid terminating it, but this only makes sense for syncing purposes. You can easily conclude here that they don't provide authentication, encryption, and therefore their security level is close to zero. Oh, right. There is one thing I need to mention about security. It's actually something they say in the specs. They say that at critical installations, interconnected nodes should really check each other's IP addresses, thereby significantly raising the level of security. I don't even know whether anyone present in this room can ever spoof that. So Modbus functions are broken into three groups. Some functions are standardized, some are user-defined, and some are used for diagnostics. And user-defined functions can be used diversely, differently by developers, by programmers who actually program PLCs, programmable logic controllers. Standard functions include two subgroups. One is data access. That certainly is the key function of a sensor like this. So the read-write coils and registers and file records, and also they have diagnostics functions. In fact, these are numerous functions, but they will differ from different channels, from one channel to another. In TCP/IP, for example, device identification is what's really important to us. According to the standard, devices should disclose vendor names, product codes. Actually shown in bold is what they should provide every time, and optional data is shown in regular font. Well, in fact, there are still differences between how they provide this information. Well, this screenshot, a well-known program, shows the results of a scan of a small network with Schneider Electric controls, and you will see that all of them talk about themselves and their firmware version. Below that, you also see Cisco CGS. But the Cisco device actually disclosed a different amount of information. So the standard response doesn't tell you much. It maintains this information but in a separate segment. I assume that pretty much everyone has worked with a Modbus. After all, there are so many emulators out there. There are also utilities for scanning, fuzzing, for device discovery. For example, ModScan is quite popular. And PLC Scan, I actually wrote PLC Scan, so I can't fail to advertise it. I actually think the utilities are not that good. I think that Wireshark can be even better. Or you can use Python. I prefer Python, though other languages are also a good possibility here. Let me show you now a short demo. Okay, this video shows what you can do with Modbus. This is what we showed during the workshop, and you can still watch it today in front of the stage. So we operate a crane, or rather the operator should control the crane, but it is essentially connected to the controller via some simple Chinese RTU. SCADA is controlled, is protected with a password, but we have a bad guy. He can easily bypass it. So he gets control of the screen, probably of the crane, So you see that now the bad guy is essentially operating the crane. And you will see that we are pressing no buttons there on the operator's station, but the crane is moving. So if the operator sees it, he can probably intervene, although with a serious chance of actually breaking the crane by issuing different conflicting commands. And you'll see that the bad guy has set his operating registers to 1, which means that the operator's workstation has gone haywire, and all their channels are inverse now. Let's discuss S7 protocol. We call it Mystic S7, and we call it Mystic because it is weird in a way. You know, I've spent so much time reading Siemens docs, and I can tell you that the stuff you see on a 102 TCP port, it actually tells you it's ISO on TCP and even refers to RFC 1086. But this is a picture I found somewhere on Siemens forum that actually tells you where RFC 10006 sits. It essentially sits over, it sits in the transport layer, which means that S7 protocol actually works below it. It's a nice picture. Obviously, we are not the first guys to start working on Siemens protocols. Before us, Dylan Beresford made a great research into it, and in his research he actually discovered a number of vulnerabilities of the protocol, but he only showed them as replay attacks. He didn't really look much into traffic. He just captured the traffic and then he reproduced the traffic. Well, we decided to look more into the details of the traffic, of the protocol, We were not the first in this respect, because Wireshark Dissector was the first one to do that. You can follow this link, and I think that they actually do a very good job dissecting the protocol, although you can argue that they could have done an even better job of it. And certainly they don't cover all the models. Also, there are some libraries, some are open source, others are not, that were developed for engineers, SCADA engineers primarily, so that they could ensure compatibility of Siemens with other devices. In fact, all of them were reverse engineered. Well, claiming that any of these libraries is the full representation of the protocol would be a bit too far-fetched. LibNDave is the best known one. You can easily download it. It's open source. Okay, let's look at ISO and TCP RFC 10006. This is essentially a transport layer. It's a transport protocol responsible for establishing connections. Well, you can argue TCP does connections as well. However, ISO and TCP establishes a connection over TCP. And they need it because you can have several devices running off a single IP address. This is what's happening there. We have a CPU and a communication processor using the same IP. TCAP stands for Transport Service Access Point, and the second digit there tells you the slot ID. Well, the first digit describes the connection type. 01 describes the programmator, while 02 is the operator station. So depending on the type of the connection, this or that function will or won't be available. So this particular Siemens Series 300 actually supports both types of connections, while 400 series only support operator stations. This is as much as we were able to find in the official docs. Actually, we know that other IDs are possible. This TCAP can actually be not 2 bytes, but can be longer. What that means, we're still struggling to learn. What's under ISO on TCP? Actually, you will remember from the picture that it sits on top of the so-called S7 protocol, and you will see here 3 dumps of, in fact, similar packets. They are similar in terms of their function, but they look very differently. You will see that they all start with protocol IDs, and they are all different. The first one is 5335, which is actually read as S5. This is the well-known protocol called Fetch Write, SANAC H1, and S5 communication. And this protocol is designed to assure compatibility with Siemens S5 devices. Next one is S7. I'm sorry, some of this actually don't support S7 devices. It's an old protocol, really, and pretty boring one at that. Next one starts with 32. This is a protocol for S7 communication. LibnoDave was developed for this particular protocol. Same goes for Wireshark, etc. There is also another protocol that starts with 7201. And you will usually see it when connecting NTR portal to the certain model of Siemens. We have not really found any real references to this particular protocol. That's why we call it another S7 communication. If Siemens has a problem with it, we are prepared to rename it. Now we are going to talk about the second one that started with 32, which we shall refer to as the vanilla S7 communication. We're interested here in several PDU types. So parameters obviously depend on PDU type, and data depends on parameters. So these PDU types are possible: request, acknowledgement, response, and user data. User data is actually the thing that enabled Siemens to encapsulate yet another protocol in the whole shebang. They essentially move the parameter into the data field, and it carries yet another payload there. I don't know why they did that. Maybe because they just wanted to develop this protocol and they just use it as a crutch, really. Or maybe it's responsible for some other modules. So what can we do with S7? Obviously, it supports access to data, which we can read or write. We can do starts and stops in internal memory. So we can start, stop CPUs of operator stations. And we can upload, download blocks in engineer stations. So all these functions will be made available via requests, while the other functions will be available based on user data. So you can get, for example, lists of blocks, and you can also read system status list. It's called SZL. I can only guess it comes from some German name for system status list. And from SZL you can learn more about LED status, component identification, module identification. Well, LEDs are fun, you can blink them, but most importantly, by accessing their status, you can actually learn more about the actual status of the PLC itself, whether it's started or stopped.
Сначала device identification. Собственно, опять-таки, utility PLC scan за моим авторством.
PLC scan, which is my utility, can actually give you such identification data for 300 and 1200 PLCs. You'll see that for 300 device you get much more information, but still in both cases you can read the firmware version and the device ID. Well, Siemens actually knows of some vulnerabilities of its models, and more exploits are available. We also have a short demo we are going to keep till the end of my presentation. Now, Sasha, I'm sorry. In Series 300, they have password protection. In fact, there are 3 protection levels for PLC. One could be 0 password, another is write password, and also a password for write and read operations. Interestingly, the last password can only protect you only so far. You can start and stop the device easily without any need to enter the password. So this is what the authorization packet looks like. Again, it starts with user data in PDU, and then the password is transmitted like this. Dissector actually identifies it for what it is. It doesn't really look like a password, right? You can't really call it encryption. You can call it obfuscation. Let's look at the obfuscation algorithm. It's very simple. This is essentially an authentication package. And I would assume that with this authentication, they also update the firmware there, and a new password is established. So it's pretty easy to capture it. You'll see that there is the constant there is 0x55, and in the firmware it's 0x88. But this is it. This is the only difference. In Miami at one conference, a guy named Johansson made a similar report. Unfortunately, I didn't go to Miami, and I saw the video only last week when the presentation was finished. So here we have this particular, a link to Eric Johansson's movie on digital bond. Finally, let's look at the differences between the protocols. So on 300 PLC, we can read and write variables, we can start stop CPU, we can upload, download blocks. With 1200, we can only read write and do device identification. You can ask us, well, what about the rest? Well, you can argue that the new device, 1200, is more secure and it's simpler at the same time. Well, we would argue, though, that all these functions are in fact kept in another S7 communication, and Alexander will tell you more about it now. We're interested in PLC protocols because we are security guys. We wanted to learn more about passwords and protection there. What you see in the screen is a traffic dump we captured as a PLC was trying to establish a connection with the engineering station. That ran Siemens software called TIA Portal. Another S7 can easily be identified by 7002 hex identifier. And you will see that it sends such information as name of device, workstation. session data. Dima has already mentioned that TIA portal is either not protected at all, or you can have password protected read or read and write. I'm sorry, password protected write, password protected read and write operations. Which means that all the functions you see in the bottom part of the slide are not really protected. Okay, how do we store the password on the TIA portal site? Essentially, it is all stored in the same file, and in fact all the previous passwords are also stored in the same file. Finding the password is very easy. Essentially, you just rehex it, and this is it. And you'll see that it was actually hashed using a simple SHA-1 algorithm. After we found it in the project file, we realized that the next non-zero byte suggested the length of the password, and this is 3 in fact, and they multiply and they calculate using the formula below. And you can look at constants like C280 in order to learn more about the password. Then we developed a simple utility that would extract hashes of passwords, and you can actually find it on Google Code. We can also extract SHA hashes of the passwords while PLC is in work. Now there is this protection on PLC from unauthorized access. But again, it's a very simple type of protection. They're using B64 over SHA-1 on Unicode. Next we'll look at authentication between the engineer stations, which I will call it SCADA, and PLC itself. So when a device is initiated, when for example you start the CPU, the PLC gets a request for authentication. We respond with a challenge. SCADA, based on the password, calculates the response, sends it to PLC, and in response we get authentication results. So what you see here are the packets where you can find challenges and responses. Well, to that end, a very simple utility was developed. So this simple utility extracts challenges and responses from the traffic dump and can brute force the password. Well, ICS CERT published a small alert on that, and John the Ripper produced a jumbo pouch that can easily extract challenges and responses and brute force the rest. Then Digital Bond also published a small short article on extracting passwords from traffic dumps. And you see here a simple illustration of how this utility works. Please note that in order to obtain the password, or rather the hash of the password you got from traffic, you need to know whether authentication attempt was successful or not. And you can learn that by looking at the length of the packet and looking at the signature provided on the screen. Please note as well that Dylan Beresford also studied this protocol, and Dima has already mentioned it. He even wrote specific modules for Metasploit, but I don't think they actually cover this particular application. Let's look at Profinet, which is another very popular protocol. In fact, it's not just a single protocol, we're talking about a whole family of protocols here. It is used to help PLCs liaise with engineering stations among each other. It was standardized in 2003. I haven't been able to find this protocol in public access. Must cost a lot of money, I assume. It's based on two concepts, Profinet CBA and Profinet IO. The first one is used to breach PLC modules, and Profinet IO is mostly used to support interaction between PLCs and RTUs. Well, the first one, CBA, is based on TCP/IP, while Profinet IO initially went on industrial Ethernet. Now it's using Ethernet, so it remains at layer 2. Profinet IO works in master-slave mode. They can talk over a common bus. Okay, response time is around 10 milliseconds. There is also time syncing protocol or time control protocol, and discovery and basic configuration protocol for Profinet is mostly used to diagnose devices and for the purposes of simple configuration. Here you will see traffic dump in DCP, and again Wireshark can easily dissect it. After we analyzed this protocol, we developed a simple utility which can sit in a single segment of the network and discover all devices that support it, and this will include HMI and PLCs and engineering stations. With a scanner like this, we can get data like station name and network characteristics such as IP address, mask, gateway. Profinet DCP scanner. So it uses multicast requests, and it carries a payload like this. So the first 2 bytes. Okay, we'll go faster. The first 2 bytes are used as an identifier of the DCP protocol. Then 1 byte identifies service. Next byte is a request type. Then 4 bytes are used for request identifiers. And next we have the allowable response delay. And next, data block size or data length, and then we actually get the options we requested. Well, here we requested all the options and sub-options. DCP can help us change the name of the station, or change network configurations, or request network configuration. We can flash the LEDs. In order to signal some problem with PLC to the engineer, for example. We haven't heard the official response from Siemens yet. You certainly know that S7 is a proprietary protocol. You know, Rob Savoy's presentation helped me a lot. The key idea there was that if you stare at the hex dumps long enough, you will start to see patterns. You know, dividers, ASCII lines, and so on and so forth. So there is also a utility called NetZop that simplifies analysis of proprietary protocols. We didn't use it though, we only used fuzzing. We, for example, developed a fuzzer for Profinet DCP protocol, which can actually test the reactions of PLC to different fuzzers. And shown here are the key utilities we used. In conclusion of my speech, or rather our speech, I'd like to point out that our team collected quite detailed statistics on different SCADA systems, their vulnerabilities, and you certainly can read more if you follow this particular link. Also, if you're interested in SCADA security, I suggest you visit SCADA Strangelove, ISA CERT, and several others that they're shown there in the recommendations section. By the way, all the utilities we've developed are publicly available of Google Code. We would also like to use this opportunity to thank our whole team, particularly SCADA Strangelove. Now we shall be happy to take your questions, and we shall also be available via email throughout the day today. And we also wanted to show you a short live demo. I'm sorry, there must have been a neutrino attack or something in the morning. I'm not sure it's going to work fine. I haven't been tracking the moon calendar, but it sounds like we have some space activity period happening now. Okay, you see the PLC on the table. It's Series 300. Experts tell me it costs a whole fortune. I don't know. I didn't buy it. Some friends brought it to me from some plant where they said it was gathering dust. So we're sitting on the same network with this PLC. We are connected through a regular switch. So let's first introduce ourselves. I'm sorry, I forgot to turn on the video. Okay, so you see the PLC here on the video, and you see a number of LEDs on the PLC. Well, this essentially means that it has been started. You are not going to see much on the console, right? Okay, we're introducing ourselves. Okay, PLC scan is working. So it tells us that this module is 6ES7314 and so on and so forth. It actually gave us a name that's much easier to read. It gave us the vendor and serial numbers. Cool. Now we know who we're dealing with. Let's try doing something with it now. Well, let's look if it has a password. Let's see if it has a password. So here I show TSAP and IP address for it that I got from PLC scan. So we brute forced it. They have a very short dictionary, like 10 lines. And we got the right password, which is security, so it's protected with a password. Okay, let's move on. Okay, so I wrote stuff in internal memory.
отреагировал на некоторый триггер и начал выполнять какую-то программу.
So you see that it has reacted to a certain trigger and is now performing its own program. Moreover,
Так, теперь ну что? Картинка. Дальше в консоли больше ничего не буду делать.
I'm going to do much
Более того,
in
мы
the console,
можем
I think.
напрямую взаимодействовать на выходы.
Actually, now we're going to
Выходы, вот когда тухнет, видите, тут лампочка.
deal with the outputs. You see? You must see the lamp blinking there, right?
Пишем выход из PLK, то есть если к ним что-то подключено, то
It actually shows that if something is connected to the outputs, then there will be this running green light over there.
Кроме того, мы можем остановить ЦПУ. То есть вот сейчас
We can even stop the CPU. So you can see the state of LEDs there, and the run lamp is on. Let's try stopping it. This is it. The CPU has been stopped. And the console now tells us the same. And you will see now this orange LED on the left. We have restarted it. You must have seen the lamps on the left blink several times, and now the CPU has been started.
Ну и теперь была демонстрация, но, к сожалению, она прошла раньше времени, когда мы только включили электричество. Кто здесь был рано, видел. По идее, мы сейчас подали на отдельный выход, и у нас должны были сделать бабах, два конденсатора подключенных.
I'm sorry, the best part of our presentation that involved blowing up to condensate